Welcome to Telli Bear's Techy Tidbits, lovingly hosted by AI. AI is incredibly powerful, And as it grows at this breathless pace, engineers are realizing they need to completely rethink something fundamental about how computers are actually built. It all comes down to saving energy. So, in today's explainer, we're exploring a tiny new device. It's directly inspired by the human brain, and it could change how AI uses energy in a truly big way. Let's get into it.
Section 1. The Endless Digital Commute.
Okay, to understand why we even need a completely new kind of chip, we first have to talk about the exhausting digital commute happening inside your devices literally right now. Just imagine you're cooking a massive, complicated feast. But there's a catch. Your stove is in one building, and your refrigerator is in a totally different building down the street. It sounds awful, right? Well, that brilliantly illustrates the problem with most modern computers. In this analogy, the stove is the processor where the cooking or thinking happens, and the fridge is the memory where all your data ingredients are stored. Every single time a computer thinks, data has to make this commute, just constantly running back and forth over and over again. This is known as the von Neumann bottleneck. It's an architectural design that dates all the way back to the 1940s. Now, it's not a crisis, but it is a fascinating design puzzle. Because as AI grows, this digital commute gets busier and hotter, wasting a tremendous amount of energy just shuffling data around.
Section 2. Nature's Perfect Computing Blueprint.
So, scientists are starting to rethink this commute itself. And to do that, they're looking at nature, because nature actually already solved this puzzle. See, the human brain doesn't have a separate stove and fridge. It stores and processes information in the exact same place at the exact same time. The memory is already woven into the thinking itself. No commute needed. This brings us to an exciting field called neuromorphic computing, basically brain-inspired hardware design. Now, a really important misconception we should clear up right away. Scientists are not trying to build sci-fi artificial minds here, or recreate human consciousness, not at all. They are simply studying biology's incredible physical efficiency so they can eliminate that digital commute. Building stable, reliable, artificial versions of brain cells proved incredibly difficult. Honestly, that was the real challenge all along.
To truly appreciate nature's blueprint, consider this frankly astonishing fact. Your brain handles vision, movement, complex memory, deep emotion, and rapid thought all simultaneously. And it does all of this on roughly the power draw of a standard laptop charger. It's wild. Your brain uses these tiny voltages, around 1.0 volts or even less for its signals. It relies on neurons and synapses working together absolutely seamlessly, which provides an incredible roadmap for low-energy computing.
Section 3. The Cambridge Memristor breakthrough. Which brings us to a major leap forward. In a 2026 study published in Science Advances, researchers at the University of Cambridge announced a breakthrough using a tiny component called a memristor. It mimics how biological synapses work. Think of a memristor kind of like a door that perfectly remembers exactly how many times it's been opened, even after you turn the power off and leave the building for the night. The Cambridge team made this artificial synapse out of hafnium oxide, which is a ceramic-like material. But they engineered it down to the atomic level, carefully adding very specific metals like strontium and titanium for extreme precision. The really crucial point here is how this differs from what came before. Older memristors relied on conductive filaments. Imagine tiny, unpredictable lightning bolts just constantly growing and snapping inside the material at high voltages. It was chaotic. But the Cambridge team completely swapped out those erratic lightning paths for smooth, reliable, and highly controlled electronic gates at the material's interface. It's a completely different approach. To ground this in the science, let's look at a quote from the lead researcher on the project, Dr. Babak Bakheith. He points out that because their devices switch at the interface, they show outstanding uniformity. That smooth, reliable interface is exactly what allows the device to support the hundreds of stable, multitasking levels of electrical flow that advanced AI absolutely needs to function efficiently. Section 4. The Reality of Manufacturing. Now, it's really important we take a calm, honest look at what this all means. As much as we love exploring brilliant lab prototypes, there's almost always a gap between a breakthrough in a lab and real-world mass production. It's the ultimate question. Can we actually build this at scale right now? Well, the honest answer is that while this tech could one day make AI viable in ultra-low power settings, think remote environmental sensors or even medical implants, there is a significant catch we have to overcome first. And here is that catch. Currently, the biggest hurdle is heat. To fabricate this specific hafnium-based chip, the process requires temperatures around 700 degrees Celsius. That is simply way too hot for standard modern semiconductor manufacturing, which prefers much cooler conditions so it doesn't accidentally melt all the other delicate components on a chip. We want to be completely transparent in this explainer. The core challenge isn't just the extreme temperature itself. It's about figuring out how to weave that intense heat process seamlessly into the highly delicate existing chip fabrication methods. So yes, the research and the final consumer products are at very different stages right now, but importantly, the Cambridge team is actively working on bridging that exact gap to make it compatible with modern factory lines. Section 5. Rethinking computing from scratch. Stepping back for a moment, this breakthrough is just one vital piece of a much larger puzzle. It's part of a growing, ground-up movement within the engineering world to rethink computing architecture entirely. If these manufacturing hurdles can be cleared, we're looking at the theoretical possibility of up to a 70% energy savings in AI hardware. Just imagine what those kinds of savings could mean. It could drastically lower the climate impact of massive data centers and broaden access, helping to decide who gets to actually afford and use powerful AI tools in the future. Bringing our kitchen analogy full circle, imagine a world where that exhausting digital commute is finally removed. The stove and the fridge are combined, and the ingredients are exactly where the cooking happens. By tapping into the millions of years of natural research and development that went into the human brain, we are opening the door to an incredibly exciting, highly efficient technological future. If there's one thing you remember from this, let it be: the most powerful computer we know of runs on roughly the power of a laptop charger, and we're only just starting to take that seriously. Thank you for listening to Telli Bear's Techy Tidbits. I hope you have a magical day. Stay curious, stay kind, stay safe.